Beneath the cold, steel-blue surface of the North Pacific, the water is alive with flickers of silver. Herring schools drift like restless clouds, shifting shape in seamless waves as though controlled by some invisible hand. To a predator, however, these shimmering shoals are not infinite. They are wealth tightly packed into nervous spirals, energy compressed into muscle and oil, waiting to be converted into the fuel of migration. For the humpback whale, a creature that can stretch nearly as long as a city bus and weigh as much as 40 cars, the trick is not locating prey, but capturing enough of it to justify the enormous metabolic demands of its bulk. To feed efficiently, the humpback must turn the chaos of the shoal into a harvest that can be swallowed whole. And to achieve this, it relies on one of the ocean's most spectacular forms of cooperative strategy: bubble net feeding. From below, the first sign is a trail of pearls. A single whale begins the process, spiraling upward in a controlled ascent. Air streams pour from its blowhole in long, deliberate exhalations, creating a rising curtain of bubbles that ascend like a cylindrical wall through the water column. To fish, those bubbles are a barrier. The herring do not perceive them as harmless gas pockets, but as turbulence, a change in pressure, a disruption in the orderly signals of light and motion they use to navigate. Startled by this barrier, they tighten together, abandoning the safety of dispersion for the illusion of strength in density. This is the opening act, the construction of the bubble net itself. But the hunt does not belong to one whale alone. Around the perimeter of this watery trap, companions are already moving into position. Humpbacks are not silent hunters. They communicate constantly through low-frequency calls that can travel for miles, their rumbling songs layered with clicks and pulses. Within the net, however, sound is not art. It is a tool of precision. The whales coordinating this performance use specialized feeding calls, a kind of rallying cry that synchronizes their movements. The sound herds the herring just as effectively as the bubbles, pushing them toward the tightening core of the net. In effect, air and sound combine to form an invisible corral, a moving fortress constructed in the open sea. Physics sharpens the trap. As the bubble net rises, water pressure decreases, and the bubbles expand, thickening the wall. At the same time, the turbulence generated by the rising air creates an upwelling current that forces the fish upward, compressing them into an ever denser ball. Herring that might once have darted in dozens of directions now find escape paths blocked on all sides, bubbles on the perimeter, whales below, and open air above. They are caught not by force but by geometry and physics. It is a living funnel with a single inevitable exit, the waiting mouths of the whales. Then comes the climax. From the depths, multiple humpbacks rise in unison, mouths agape like enormous blue caverns. Their throats expand outward, pleats of blubber stretching to create cavernous gulps capable of engulfing tens of thousands of liters of water and fish in a single strike. The sound is muffled in the ocean, but the visual is explosive. A column of whales bursts through the compressed shoal, water cascading from their jaws as herring pour inward like loose coins into a purse. Gulls wheel and dive at the surface, stealing fragments from the chaos, but the majority of the feast disappears into the cavernous gullets of the whales. The mechanics of feeding are extraordinary. Humpbacks belong to the baleen whales, filtering feeders equipped not with teeth, but with racks of keratin bristles that hang from their upper jaws like a comb. After each lunge, the whale closes its mouth and uses its massive tongue to push water through the baleen plates, straining out the fish while releasing the spent seawater. What remains is a dense slurry of prey, hundreds, sometimes thousands of herring swallowed in a single motion. This efficiency is critical. For a humpback whale, energy economics dictates survival. A single lunge consumes tremendous energy: the acceleration, the drag of an open mouth, the expansion of the throat pleats. If only a handful of fish were captured, the whale would lose more energy than it gained. But bubble net feeding tips the balance. By coordinating to corral vast numbers of prey at once, the whales transform each lunge into an overwhelmingly profitable transaction. To understand the scale, one must consider the mathematics of energy. Chasing individual fish, a humpback might capture only a few calories per strike. nowhere near enough to sustain its 70,000-pound frame. But with a bubble net, it can engulf a school numbering in the thousands, yielding millions of calories in seconds. When these whales feed, they're not merely eating, they're banking energy to fuel one of the longest migrations of any mammal, journeys that span from polar feeding grounds to tropical breeding waters thousands of miles away. The bubble net is not simply a trick of predation. It is a survival system designed to convert fleeting opportunities into long-term endurance. The strategy also highlights a fascinating aspect of whale behavior: culture. Not all humpback populations employ bubble net feeding. It is not a universal instinct written into their DNA, but a learned behavior passed through social groups. In some regions, mothers teach calves, and groups refine their techniques over generations. This makes the bubble net not just a hunting method, but a cultural artifact, a shared blueprint of survival that binds communities of whales together. It demonstrates intelligence, communication, and social learning on a scale rarely appreciated in marine predators. The ecosystem itself feels the impact. When humpbacks compress schools of herring, the ripple effect spreads outward. Predators such as sea lions, sharks, and seabirds exploit the chaos, diving into the scattered edges of the shoals. The concentration of prey becomes a feeding bonanza, not just for the whales but for the entire marine food web. And in turn, by reducing herring numbers, whales influence the balance between fish and the plankton populations they consume. The bubble net is thus more than a spectacle. It is a driver of ecological equilibrium, a keystone interaction that resonates through the system. Even the sensory adaptations of the herring contribute to the drama. These small fish rely heavily on their lateral line system to detect vibrations and flow changes in the water. The rising curtain of bubbles interferes with these signals, creating confusion and panic. What they interpret as solid barriers are in fact shifting, transient walls of air. Their defensive schooling behavior, meant to deter predators by creating confusion through numbers, instead plays into the whale's design. In attempting to protect themselves, they compact into the very density that makes them easiest to engulf. Seen from the perspective of natural selection, the bubble net feeding strategy is a triumph of cooperative evolution. A single whale could never trap prey in this way. The effort requires choreography, timing, and trust among multiple individuals. It demands not only physical adaptations, elastic throat pleats, enormous lung capacity, sensitive hearing, but also cognitive ones: memory, coordination, and communication. In essence, humpback whales turn the tools of their physiology and the invisible forces of water and sound into architecture, creating temporary walls and ceilings that corral life itself. And so, when the ocean boils with bubbles and a column of whales erupts into the light, what unfolds is not chaos but design. Air and sound, physics and cooperation, energy and culture, woven together in a fleeting cathedral of bubbles. In those moments, the humpback whale reveals itself not just as a predator, but as an architect, a strategist, and a keeper of traditions that echo through generations. The sight may last only seconds, but beneath its surface lies a blueprint millions of years in the making, the marriage of biology and environment into a moving wall of life, one that turns the empty vastness of the sea into a trap as elegant as it is deadly. The open ocean is often described as a desert, vast, featureless, and unforgiving. Unlike coral reefs with their riot of shapes and shadows, or kelp forests with their columns of green, the pelagic zone offers little in the way of concealment. Here, light filters down in shifting gradients of blue, and predators must rely not on terrain, but on physiology and deception to survive. Drifting in this empty expanse, the barracuda appears at first like a fragment of sharpened silver. Long, lean, and built for the sudden violence of speed, it is a predator designed to thrive where cover does not exist. It does not ambush from shadows, nor chase over long distances. Instead, it waits, suspended in stillness, until a flicker of opportunity draws it into action. Then, with a motion so rapid that the eye struggles to track it, the silver blade becomes a weapon. The barracuda's reflective scales are its first advantage. In a world where open space offers no hiding place, invisibility must be crafted from light itself. The fish's flanks are composed of guanine crystals layered like sheets of glass. These crystals scatter incoming light, turning the barracuda into a shifting mirror of its surroundings. Against the cobalt blue of the ocean, the silver sheen reflects the same gradient, making the predator nearly indistinguishable until it moves. This camouflage is not static. Subtle changes in body angle adjust the way light bounces, minimizing sudden flashes that could betray its position. Marine biologists often call this glint management, a technique shared by many open water hunters. By reducing stray flashes, the barracuda masks its approach until the final fraction of a second. Hovering motionless, the fish appears almost languid. But beneath that stillness lies a physiology tuned for explosive release. The barracuda's body is essentially a series of fast-twitch muscle fibers arranged along a streamlined frame. These fibers contract rapidly, generating immense power for short bursts of acceleration. When prey wanders into range, a sardine, a small tuna, or even a hapless reef fish swept into open water, the barracuda does not hesitate. Its strike begins with a whip of the head, a sharp yaw that reorients its jaw ahead of the body. The sudden angular motion allows the predator to seize prey before the fish can initiate an escape turn. This head-led yaw is a signature of its hunting style, one that maximizes the advantage of milliseconds. The speed of the strike is difficult to appreciate until measured. In less than a blink, the barracuda can cross 3 times its own body length. For an animal that may grow to 6 feet, this means lunges spanning several meters in a heartbeat. The jaws snap shut with a force amplified by dagger-like teeth, each one angled slightly backward to prevent escape. These teeth are not just cutting tools but grappling hooks, designed to seize and hold slippery prey even in the turbulence of a strike. Once caught, few victims wriggle free. The efficiency of the attack ensures that the energy invested in the sprint is almost always returned in calories. What makes the barracuda's strategy so fascinating is not only its speed, but the sensory network that directs it. Along its body runs a lateral line system, a specialized organ composed of fluid-filled canals sensitive to vibrations in the water. Every flicker, every oscillation of a nearby fish's tail sends ripples outward. The barracuda can read these signals with remarkable precision, determining the size, direction, and even the fatigue level of its potential prey. A fish swimming erratically, perhaps injured or panicked, stands out like a beacon. This sensitivity explains a peculiar truth long known to fishermen. Wobbly lures, those that mimic the uneven flutter of a distressed fish, consistently attract barracuda strikes. The predator is less fooled by appearance than by vibration. To a lateral line tuned for survival, the wrong kind of wobble is irresistible. The open water lifestyle comes with trade-offs. Unlike reef ambushers that may feed opportunistically throughout the day, the barracuda relies on patience and precision. It does not waste energy chasing shoals across distances. Instead, it lurks, often at the edge of a school, drifting like a silver sentinel. The shoal itself offers a paradox. Prey fish form tight groups to reduce individual risk through confusion and dilution. Yet the very density of their formations allows a predator like the barracuda to cut through and isolate targets. A sudden lunge into the swarm creates chaos, scattering the formation and exposing the weak or slow. The predator withdraws as swiftly as it attacked, rejoining the emptiness of the pelagic zone until the next strike opportunity arises. Adaptations for survival extend beyond hunting. Barracuda must also avoid detection by their own predators, including sharks and larger pelagic hunters. Their reflective camouflage works both ways, shielding them from being seen as readily as it hides them from their prey. Juvenile barracuda often gather in shallow seagrass beds, where their silver sides reflect the fractured light, making them nearly invisible among the blades. As they mature, they move into deeper waters, where their speed becomes their greatest defense. The combination of optical trickery and muscular design allows them to navigate the predator-prey arms race of the open ocean with efficiency. The ecological role of barracuda is more significant than their solitary behavior suggests. By preying on mid-level fish, they help regulate populations that would otherwise overgraze plankton or reef organisms. Their hunting patterns exert pressure on schooling behavior, reinforcing the survival advantages of collective motion. In this way, the barracuda is both predator and sculptor, shaping the dynamics of the pelagic food web. Without such hunters, shoaling species might dominate unchecked, destabilizing ecosystems that depend on balance across trophic levels. Evolution has refined this predator over millions of years, producing a design so efficient that little change has been necessary. Its long, torpedo-like body reduces drag, its powerful tail provides thrust, and its jaw architecture maximizes grip. Yet beyond anatomy, the barracuda embodies a principle seen throughout marine ecosystems. Success in the blue desert comes not from raw power alone, but from the fusion of deception and speed. Camouflage makes the strike possible. Reflexes make it lethal. There is, however, a curious tension in how humans perceive barracuda. To divers, their stillness can feel unnerving. A long silver shape hanging in the periphery, teeth glinting faintly in filtered light. Tales of attacks on swimmers, though rare, feed a reputation for aggression. Yet in truth, barracuda are not reckless killers. They are specialists, honed to take advantage of narrow windows of opportunity. Their strikes are precise, not indiscriminate. What appears as menace is often only watchfulness, the same patience that governs their hunting. Still, the flash of mirrored scales and the sudden violence of their charge leave a lasting impression on any who witness it. Perhaps what is most striking about the barracuda is how it embodies the challenges of its environment. In a world without cover, it has learned to hide in light. In a realm where distances stretch without landmarks, it has mastered the art of stillness until motion matters most. And in an ocean where survival is a contest of seconds, it has evolved the ability to win those seconds decisively. The barracuda is not a brute force predator, but a blade, polished, poised, and always a breath away from release. In the end, what the barracuda demonstrates is a blueprint of survival that seems almost paradoxical. It is at once invisible and unavoidable, passive and explosive, silent and sudden. To watch one hover in the water column is to see the embodiment of restraint. To watch one strike is to witness the economy of evolution, minimal motion, maximum return. In the blue desert, where every mistake can mean starvation, the barracuda thrives by balancing patience with power, camouflage with clarity, and stillness with speed. It is a predator that does not need shadows to hunt, it makes its own. On the dim continental shelves where light begins to fade and shadows linger long, there lies a predator that looks less like a fish and more like a piece of the ocean floor itself. To the untrained eye, the monkfish is nothing more than a lump of stone, an irregular patch of mottled sand and algae-stained rock. Its body is broad, flattened, and ugly in the way only a master of disguise can be, for ugliness here is survival. But this apparent lifelessness is only a mask.
Watch closely, and you will see a single delicate movement rising above the still bulk. A slender filament tipped with a fleshy lure, waving gently as though caught in a non-existent current.
To small fish passing overhead, it resembles a worm or a shrimp. To the monkfish, it is the key to turning patience into prey. The monkfish belongs to the anglerfish family, a group defined by their unique weapon, the elysium and esker. This rod and lure system, evolved from the first dorsal fin spine, is perhaps one of nature's most remarkable biological inventions. At the end of the filament sits a bait-like structure, the esker, which can be wriggled or pulsed in patterns that mimic the tiny invertebrates on which small fish feed. In the endless expanse of the sea floor where food is scattered and shelter is sparse, the illusion of an easy meal is irresistible. A juvenile cod, a sand lance, or even a small flatfish may drift close, drawn by the promise of effortless energy. Yet what seems like opportunity is nothing more than a carefully staged trap. The moment of attack is as sudden as it is final. When prey comes within range, the monkfish performs a feat of hydrodynamic engineering. With a violent expansion of its buccal cavity, the space inside its mouth, it generates negative pressure in the surrounding water. In less than a few thousandths of a second, the seafloor inhales. Water and prey are sucked inward in a torrent too strong to resist. The expansion is powered by muscles that pull the floor of the mouth and the sides of the head outward, creating a vacuum effect. The strike is not a matter of chasing or grappling. It is suction predation at its most extreme, where the surrounding environment itself becomes the weapon. Scientists have measured this inhalation as one of the fastest feeding motions in the vertebrate world, rivaling even the tongue strikes of chameleons. For the monkfish, it means that once the prey crosses an invisible threshold, escape is no longer an option. Camouflage plays a vital role in this ambush. The monkfish's mottled skin, covered in irregular patches of brown, yellow, and green, matches the texture of sand, mud, or shell debris. Tiny fringes of skin along its jawline resemble algae fronds or stray seaweed, further breaking up its outline. Often the fish will bury itself partially in sediment, leaving only its lure visible above the surface. This burial reduces its profile to near invisibility, making the lure's motion all the more convincing. The strategy relies not on speed over distance, but on invisibility and timing. By allowing prey to come to it, the monkfish conserves precious energy in an ecosystem where food may be scarce for days at a time. This energy conservation defines much of the monkfish's existence. Living on the margins of continental shelves, where productivity varies with seasons and currents, these fish cannot afford the costly chases that define predators of the open water. Instead, they operate on what ecologists call a low-energy budget. Each ambush is a gamble, but one where the odds are tilted by careful placement and patience. By choosing habitats along edges, where rocky outcrops meet sand plains, or where currents funnel small fish across slopes, the monkfish increases the likelihood that prey will pass within range. It is a predator that calculates not in moments but in hours, positioning itself like a fisherman setting a line, waiting for the environment to deliver sustenance. The jaw mechanics of the monkfish reinforce this strategy. Unlike many predators that rely on sheer bite force, the monkfish jaw is designed for expansion and engulfment. The lower jaw juts forward dramatically during a strike, extending the reach of the mouth. Teeth line the jaw in backward-facing rows, needle-sharp and angled to prevent escape once prey is caught. Combined with the vacuum pull of the buccal expansion, this creates a near-perfect capture system. What disappears into the cavern of its mouth does not return. Even relatively large prey, sometimes nearly half the monkfish's body length, can be swallowed whole, the stomach stretching to accommodate astonishing loads. Such capacity ensures that when opportunity arises, the monkfish can capitalize fully, storing energy for the long intervals of stillness that follow. The evolutionary elegance of this hunting method becomes clearer when viewed against the backdrop of oceanic ecology. In ecosystems with dense prey abundance, predators evolve to chase, to herd, or to compete aggressively. In contrast, where prey is dispersed across wide, sparsely populated seafloors, strategies of patience and efficiency prevail. The monkfish represents this latter model. By disguising itself as part of the habitat and creating its own illusion of prey through the esker, it bends the scarcity of its environment to its advantage. Each successful strike represents not just a meal, but the culmination of hours or even days of strategic positioning. Evolution has turned stillness into a weapon, deception into sustenance. The sensory world of the monkfish also plays a role in its predatory mastery. While its eyes appear small compared to the bulk of its head, they are adapted to the low light conditions of deeper waters. Sensitive to minimal shifts in brightness, they can detect the silhouette of an approaching fish against the faint glow of the surface or the dim scatter of planktonic bioluminescence. Yet vision is not the sole guide. The lateral line system, common to most fish, allows the monkfish to perceive vibrations in the water, alerting it to nearby movement even when prey lies outside the range of sight. The combination of subtle lure motion and acute vibration detection ensures that the monkfish can time its vacuum strike with devastating accuracy. From a broader ecological perspective, the monkfish's presence influences the distribution of smaller fish communities. By preying on individuals that investigate the lure, it exerts selective pressure on prey species, shaping their behavior. Over generations, this interaction drives a delicate balance of risk and reward. Fish that avoid investigating potential food may miss genuine feeding opportunities, while those that pursue every flicker increase their risk of predation. This tension enriches the evolutionary arms race of the seafloor, where deception and caution continuously recalibrate survival strategies. Though it may seem a solitary hunter, the monkfish also connects to human economies in unexpected ways. In many regions, particularly the North Atlantic, monkfish are a valued food species, their firm flesh marketed as poor man's lobster. This exploitation raises questions about sustainability, as their slow, patient lifestyle and relatively low reproductive output make them vulnerable to overfishing. Ecologically, the removal of monkfish alters predator-prey balances on continental shelves, reducing predation pressure on mid-level fish and potentially reshaping benthic communities. Thus, the monkfish's importance extends beyond its own survival into the fabric of marine ecosystems and human commerce alike. Perhaps what makes the monkfish most remarkable is not the violence of its strike, but the elegance of its restraint. It is a predator that has chosen, through millions of years of adaptation, not to chase, not to tire itself in endless pursuit, but to wait, to deceive, and to master the mechanics of pressure and flow. It demonstrates that survival in the ocean is not only about speed or strength, but about the patient engineering of opportunity. To witness a monkfish inhale a fish whole is to glimpse the intersection of physics and biology. A vacuum turned into a weapon, stillness transmuted into power. In the stillness of the seafloor, where rocks lie scattered and currents whisper softly through the sand, the monkfish waits. Its lure sways with a deceptive innocence, its body merges with stone and silt, and the water holds its breath. Then, in a fraction of a second, the ocean itself seems to inhale, and the illusion of safety vanishes into the cavernous mouth of a predator that has perfected patience as a way of life. The mangrove channels of northern Australia and Southeast Asia are deceptively quiet at slack tide. Water settles into a glassy stillness, its surface broken only by the glint of insects and the occasional ripple of a mullet flicking at the shallows. Roots twist down like the legs of an ancient cathedral, forming shaded corridors where crabs pick at detritus and herons watch with statuesque patience. Beneath this calm, however, lurks a predator that has mastered the art of waiting for the tide to tip in its favor. The saltwater crocodile, largest of all living reptiles, lies motionless at the edge of current and shadow. It is a reptile that has survived largely unchanged for over 200 million years, and its patience is more than endurance. It is calculation. It waits where mangrove shade meets tidal flow, reading the subtle language of water itself, until the moment comes to turn stillness into sudden, brutal momentum. The saltwater crocodile's hunting strategy hinges on a biological toolset as refined as any sonar array. Along the surface of its armored snout lie hundreds of tiny black dots, known as integumentary sensory organs. Each one contains bundles of pressure-sensitive nerves capable of detecting minute changes in water movement. The flick of a mullet tail, the vibration of a crab scuttling across mud, even the faint turbulence of a fish turning upstream, all send ripples through the water. To the crocodile, these disturbances are as clear as beacons. Unlike predators that rely heavily on vision or smell, the crocodile hunts in a medium where murk, shade, and turbidity often conceal its prey. By reading pressure ripples, it knows not only the presence of life, but its direction, speed, and size. This sensitivity allows the crocodile to hunt even in complete darkness, when mangrove channels become ink-black corridors. But knowing when and where to wait is equally important. Saltwater crocodiles are not random hunters. They choose ambush points with precision, often stationing themselves at creek mouths or tidal passes where currents funnel prey into narrow routes. Fish riding the outgoing tide, piglets venturing to drink, even unwary waterbirds foraging along the banks, all must pass through these choke points. By hugging eddy lines, the crocodile minimizes its own exposure, while maximizing its chance of encountering prey swept along by the water. The ambush is not brute force, but geography turned into a weapon. By owning the gate between open water and tidal creek, the crocodile forces the ecosystem itself to deliver meals into its jaws. When the strike comes, it is sudden and devastating. For hours, the crocodile may remain nearly invisible, its body submerged with only nostrils and eyes above the surface, a floating log among mangrove shadows. Then, without warning, it launches forward in a burst of speed that belies its bulk. The mechanics of this explosion rest in the tail. Thick with muscle and capable of generating immense thrust, the tail propels the crocodile in a lunge powerful enough to drive its armored body clear out of the water. This is leverage born of stillness, every ounce of stored potential converted in a single stroke. Its jaws, powered by muscles capable of delivering the highest recorded bite force among living animals, snap shut around the target. Escape is virtually impossible. Once seized, the prey is dragged into deeper water, where rolling, spinning motions known as death rolls disorient and drown before consumption begins. The crocodile's ability to shift between stillness and violence is only part of its mastery. To dominate such vast coastal territories, it must also navigate the challenges of thermoregulation and salinity. As ectothermic reptiles, crocodiles depend on the external environment to regulate body temperature. Too much heat and enzymes denature, too little and digestion halts. By moving between shaded mangroves, sunlit sandbanks and open water, the saltwater crocodile fine-tunes its body temperature throughout the day. Remarkably, this thermoregulatory discipline allows them to endure long voyages along coastlines. Salt glands near their tongues excrete excess salt, enabling them to travel across brackish estuaries and even open ocean. Documented individuals have crossed stretches of over 100 kilometers of open sea, riding currents and hugging eddies to conserve energy. It is no accident that they are found across vast ranges from India to northern Australia. Their physiological toolkit makes them not just river predators, but maritime rulers. These coastal voyages add a layer of complexity to their ecology. Saltwater crocodiles do not merely ambush within their home creeks, they are also capable of large-scale territorial patrols. Males in particular, which can reach lengths of over 6 meters and weights exceeding 1,000 kilograms, maintain vast domains along rivers and shorelines. By reading tides and currents, they can position themselves at strategic estuary mouths where nutrient-rich waters attract shoals of fish and seabirds. In this sense, the crocodile's ambush is not limited to a single attack, but is integrated into a larger spatial strategy, owning not just a choke point, but entire networks of them across its territory. From an evolutionary perspective, their body plan is a lesson in resilience. The heavy armor of osteoderms, bony plates beneath the skin, not only shields them from attacks but acts as a heat sink, absorbing and storing warmth during sunbathing that can later be released into the blood. Their musculature is specialized for bursts of power rather than endurance. This explains why they can accelerate so violently from stillness, yet tire quickly if forced into prolonged pursuit. Unlike marine mammals that depend on sustained chases, crocodiles play the long game, stillness until opportunity, then one overwhelming strike. Perhaps the most astonishing element of their ambush strategy is the timing. Slack tide is not merely an interval of still water, it is a biological pause in the estuarine cycle. Fish activity diminishes, crabs retreat, and many animals hold their position awaiting the shift. In this pause, prey becomes predictable, stationary, suspended in anticipation. For the crocodile, this is the moment of maximum advantage. With prey less alert and the water calm enough to detect even the faintest disturbance, the predator knows the odds are tilted in its favor. In this way, the crocodile does not simply wait at random, but reads the rhythms of the tide itself, syncing its hunt with the pulse of the estuary. The ecological consequences of such predation ripple outward. By controlling access to waterholes and tidal creeks, crocodiles influence the behavior of a wide range of species, from fish schools to terrestrial herbivores. Their presence at choke points can deter herds of wallabies from drinking until safer hours, shift bird foraging patterns, and restructure the very flow of energy through mangrove systems. In many ways, the saltwater crocodile is not just an apex predator, but an ecosystem engineer, its choices of ambush shaping the movements of countless other organisms. Humans too are part of this equation. In coastal villages across northern Australia and Southeast Asia, crocodiles are both feared and respected. Fishermen must time their work with awareness of tides not only for navigation, but to avoid the silent hunters waiting at creek mouths. The danger is real. Saltwater crocodiles have been responsible for more human fatalities than any other reptile. Yet this danger is not reckless aggression, but the inevitable outcome of shared choke points. Where people seek fish and water, so too does the crocodile. The tide delivers life to both. In the end, what makes the saltwater crocodile extraordinary is not its size, nor even its power, but its precision. It is an animal that reads the water like a language, sensing pressure ripples, watching tides, and choosing ambush sites with a strategist's patience. It does not need to chase, for it has learned that the ocean and river themselves will deliver prey. By mastering geography, physics, and timing, the crocodile owns the tide gates of its world. And when slack water stills everything else, its strike becomes inevitable. The Pacific kelp forests sway in a rhythm that mirrors the tides, vast emerald curtains rising from the sea floor toward the sunlit surface. These forests are nurseries, fortresses, and feeding grounds. Their dense fronds sheltering schools of fish, soft-bodied invertebrates, and 1,000 smaller dramas of survival. Hovering above the canopy, shafts of light fracture into golden columns, turning the forest into a cathedral of swaying life. Within this cathedral drifts an animal both charming and formidable, a predator that wields intelligence as deftly as claws. The sea otter, floating belly up on the surface, cradles a rock on its chest. In its paws, a clam writhes futilely against what it surely does not recognize as a tool. Then, with a sharp strike, shell meets stone, and the prey's fortress gives way to the otter's patient persistence. This is no simple trick of dexterity. It is a cultural and ecological signature, one that has reshaped entire marine ecosystems. Sea otters are one of the rare non-human species to use tools systematically. While many animals employ rudimentary objects in hunting or foraging, otters carry a personal toolkit, often using the same stone across multiple meals. Some have even been observed storing these rocks in folds of loose skin under their forearms, creating a kind of biological pocket. This tool use is not uniform across the population. It varies regionally and is passed down through generations. A young pup learns not just what to eat, but how to open it by watching its mother. Some otters specialize in cracking open sea urchins, others in prying mussels from rocks or smashing crabs to pieces. This specialization reduces competition within the population and reveals a cultural mosaic where different groups refine distinct feeding traditions. In this way, the otter's intelligence is not only personal but communal, knowledge spread through observation and inheritance, shaping the predator's relationship with its prey. Yet to thrive in the frigid waters of the North Pacific, tool use alone is not enough. Unlike most marine mammals, sea otters lack a thick layer of blubber. Instead, their survival depends on fur, the densest fur of any animal on Earth, with as many as 1 million hairs per square inch. This extraordinary coat functions not by insulating like blubber, but by trapping air. Each hair shaft interlocks with its neighbors to form a water-repelling barrier that keeps the skin dry and maintains a layer of warmth. But such a system requires constant upkeep. Otters spend hours each day grooming, fluffing, and combing their fur to prevent it from matting and losing its insulating air pockets. Without this relentless care, cold water would seep to the skin and chill the body within minutes. Grooming, then, is not vanity but survival, a discipline as vital as feeding. Every dive, every meal, every rest on the surface is punctuated by a ritual of rolling, rubbing, and blowing air into the fur, a daily choreography that keeps death by hypothermia at bay. This delicate balance between feeding and thermoregulation shapes otter ecology in profound ways. Because their bodies burn energy so quickly to maintain heat, otters must consume a staggering amount of food each day, up to a quarter of their body weight. To fuel themselves, they scour the kelp forest for calorie-rich invertebrates. Urchins, clams, crabs, and abalone all fall within their menu. But this appetite, coupled with tool use, positions them as keystone predators in coastal ecosystems. Their influence extends far beyond their own survival. By preying heavily on sea urchins, they prevent these spiny grazers from multiplying unchecked. Left uncontrolled, urchins can devastate kelp forests, stripping entire regions down to barren urchin barrens, where little but algae-coated rock remains. Here lies one of the most compelling ecological stories of the otter, the trophic cascade. In areas where sea otters thrive, kelp forests flourish, providing habitat for fish and buffering coastlines against storms. Where otters have been eliminated, whether by hunting in the fur trade of past centuries or by present-day absence, urchins proliferate, kelp vanishes, and the entire ecosystem collapses into diminished productivity. The otter, through the simple act of cracking shells and swallowing urchins, preserves a balance that ripples outward through every layer of the coastal web. Fish populations surge in healthy kelp, seabirds find richer feeding grounds, and even humans benefit through improved fisheries. The otter is proof that brains and tools, wielded persistently, can remake not just a meal, but a world. But this equilibrium is fragile. Otters themselves are prey to larger forces, great white sharks, orcas, and in recent decades, human activity. Their dependence on fur made them the target of one of the most intense hunting campaigns in history. By the 19th century, sea otter populations along much of the Pacific Rim had been annihilated, their pelts prized as luxury goods. With their removal, kelp forests collapsed across vast stretches of coastline, revealing the profound ecological cost of their absence. Modern conservation has allowed many populations to recover, yet they remain vulnerable to oil spills, pollution, and climate change, each of which compromises their fur's delicate insulating system. A single oil spill can coat thousands of otters, breaking the barrier of trapped air and dooming them to hypothermia. Their survival remains tied not only to their evolutionary adaptations, but to the choices humans make in stewarding coastal environments. Beyond ecological importance, the sea otter represents a fascinating study in behavioral complexity. They form loose social structures, with males establishing territories that overlap female ranges. Groups of males, known as rafts, can sometimes number in the dozens, floating together at the surface like a drifting flotilla. Pups ride on their mothers' bellies, unable to dive until they grow enough insulation and skill. During foraging dives, otters use acute tactile sensitivity in their paws and vibrissae to locate prey in murky water. Combined with their ability to manipulate tools, this tactile precision makes them one of the most dexterous marine predators. Every movement of their paws speaks to an intelligence shaped not by brute force, but by a capacity to interact with the environment in subtle, innovative ways. The kelp forests themselves, in turn, depend on this predator. Without otters, the balance tips toward collapse. With them, the forests persist as vibrant engines of biodiversity. This reciprocity illustrates a deeper truth about ecosystems. The fate of the whole can rest on the behavior of a single species. In the case of the sea otter, its survival strategies, grooming, tool use, prey specialization, extend into roles that maintain the health of entire coastlines. By restraining the appetites of urchins, they protect the towering kelp that shelters juvenile fish, absorbs carbon, and mitigates wave action. They are predators, caretakers, and unintended gardeners of the sea. It is tempting to be charmed by their playful appearance, otters cracking shells on their bellies, pups resting in kelp cradles, rafts drifting together in the sun. Yet beneath that charm lies an uncompromising battle for energy, heat, and balance. Each clam smashed against stone represents not only survival for an individual, but resilience for an ecosystem. Each hour spent grooming fur is an act of thermodynamic engineering, as crucial as any architectural blueprint. Every urchin consumed is a quiet strike in a war for the health of kelp forests that buffer entire coastlines. In the end, the sea otter is more than a tool user or a charismatic face of conservation. It is an ecological keystone, an animal whose persistence reshapes the very landscape it inhabits. It thrives not through sheer strength or speed, but through ingenuity, persistence, and the relentless refinement of behaviors passed from mother to pup. Where otters float, kelp forests rise. Where they vanish, the forests collapse into silence. Few predators illustrate so clearly how brains and tools deployed with patient consistency can preserve the very fabric of an ecosystem. In the cold Pacific waters, the sea otter is both craftsman and guardian, a living reminder that intelligence, however small the package, can wield the power to engineer worlds. At the ragged frontier where sea ice breaks against open water, a vast and seemingly immovable shape drifts along the edge. The walrus, with its heavy folds of flesh and massive ivory tusks, might at first appear as little more than a sluggish relic of the Arctic past. Its sheer size alone is enough to inspire awe. Males can weigh over 1.5 tons, rivaling small cars in mass. Yet beneath this bulky frame lies one of the most specialized and unexpectedly precise feeding strategies in the entire marine mammal world. For the walrus is not a brute force feeder, but an engineer of suction, a master of vacuum hydraulics that can transform a muddy seafloor into a buffet of hidden treasures. The secret begins with the whiskers. The secret begins. Sprouting from the walrus's broad square muzzle are hundreds of vibrissae, thick and wiry sensory hairs, so sensitive they can detect the faintest textures of the seafloor. Arranged in an orderly grid across the face, these vibrissae function like a tactile sonar array, allowing the walrus to see with touch in the turbid waters of the continental shelves. Here, visibility is often reduced to near zero. Silt and plankton clouds obscure everything, but the walrus needs no vision to hunt. It sweeps its head across the muddy bottom, whiskers raking the sediment like the fingers of a blind sculptor, feeling for the faint ridges of clams buried just beneath the surface. Each whisker bends slightly under contact, sending signals through nerve-rich follicles to the brain, mapping the invisible world of sand and shell in extraordinary detail. Once the prey is detected, the walrus unleashes a feeding mechanism, unlike any other among marine mammals. It does not rely on chewing, slicing, or crushing. Instead, it generates one of the most powerful suction forces in the animal kingdom. By withdrawing its tongue rapidly to the back of its throat, while simultaneously sealing its thick lips around the clam, it creates an intense vacuum. The pressure differential is so great that the clam's shell pops open, its meat torn free from its shell in an instant. Scientists have measured walrus suction strong enough to rip apart bivalves without breaking the fragile shells themselves, a feat of finesse rather than brute destruction. This efficiency allows the walrus to consume enormous numbers of clams and other mollusks during each dive, fueling its enormous bulk on the protein and fat hidden beneath the mud. Each feeding dive is a choreography of physics and anatomy. The walrus exhales just before submerging, reducing buoyancy, and sinks to the bottom with surprising grace for an animal of such size. Using its foreflippers to stabilize against the sea floor, it plows through soft sediments, whiskers quivering with constant feedback. A clam detected here, another there. The walrus rarely misses. Once suctioned, the remains of empty shells are left scattered across the benthos, an archaeological record of its passing. Over time, these feeding grounds resemble excavation sites, riddled with pits and depressions where clams once lay. This is bioturbation in action, the physical reshaping of the seafloor by the foraging activities of a single species. By disturbing sediments and recycling nutrients, walruses help structure entire benthic ecosystems, influencing the abundance and distribution of other invertebrates and the predators that feed on them. Walruses are creatures of the ice edge, their lives woven tightly to the seasonal rhythms of freezing and thawing seas. In winter, they rely on stable ice platforms as resting and birthing sites, while in summer, retreating ice forces them to haul out onto rocky beaches in massive, noisy aggregations. These haul-outs can number in the thousands, vast carpets of bodies heaped together, their guttural bellows reverberating across the Arctic air. Such gatherings are not merely spectacles of biomass, but crucial survival strategies. On land, walruses must conserve energy between feeding trips, and the security of numbers reduces predation risks from polar bears. Yet these mass haul-outs also carry danger, for panic can cause stampedes, crushing calves beneath tons of flesh. In this balance between safety and risk, walruses illustrate the complexity of survival strategies shaped by a shifting climate. Migration defines their yearly cycle. Walruses follow the retreating ice northward each summer, staying near the edge where access to rich benthic feeding grounds is possible. This movement is not aimless drifting, but a calculated pursuit of ecological opportunity. The ice edge is dynamic, changing with wind, currents, and temperature. By following it, walruses maximize their access to both feeding grounds and haul-out platforms. The species is thus tied to the pulse of a melting and freezing ocean, a relationship now under threat as climate change erodes the predictability of sea ice. As ice disappears, walruses are forced to crowd more frequently onto terrestrial haul-outs, altering their traditional patterns and exposing them to new dangers. The walrus's role as a benthic feeder extends beyond its own survival. By consuming vast numbers of clams and disturbing the seafloor, it helps regulate populations of invertebrates and recycles nutrients back into the ecosystem. This disturbance increases habitat diversity, creating microenvironments for worms, amphipods, and other benthic species. In turn, these communities support fish populations that are prey for seabirds and marine mammals. In this way, the walrus functions as an ecosystem engineer. It's foraging sculpting not just its immediate prey field, but entire food webs across Arctic shelves. From a physiological perspective, walruses reveal an impressive suite of adaptations to cold. Their bodies are sheathed in a thick layer of blubber that insulates against icy waters and serves as an energy reserve during long fasting periods on haul-outs. Their circulatory system is fine-tuned for thermoregulation, with the ability to redirect blood flow between the skin and core to balance heat retention and release. During dives, their heart rate slows dramatically, conserving oxygen for vital organs. These dives rarely exceed 30 minutes, but repeated throughout the day, they allow walruses to harvest astonishing amounts of benthic biomass. Their feeding strategy is less about depth and more about persistence, repeated efficient foraging in shallow waters rather than rare deep plunges. Despite their bulk and seemingly cumbersome bodies, walruses are capable of surprising agility in water. Their foreflippers act as powerful paddles, propelling them with unexpected grace through the icy seas. On land, however, their tusks become essential tools. These elongated canines, reaching lengths of nearly 1 meter, are used not only in dominance displays and combat, but also as levers to haul massive bodies out of the water onto ice. They are multi-purpose instruments, status symbols, weapons, and practical tools of survival, embodying the walrus's balance of raw strength and refined adaptation. And yet, for all their physical prowess, walruses remain creatures of precision feeding. The image of a colossal mammal delicately plucking clams from the mud with hydraulic suction captures the essence of their evolutionary genius. They are giants that thrive not through reckless predation, but through patient engineering of pressure and flow. Their world is one of tactile maps drawn in whiskers, of vacuums measured in fractions of a second, of sediments churned into mosaics that shape entire ecosystems. To stand at the edge of an Arctic haul-out, where thousands of walruses bellow and jostle under the pale sun, is to witness both the fragility and power of this species. Each individual represents a convergence of adaptations, thermal, sensory, behavioral, that allow survival at one of the harshest margins of life on Earth. But together, they represent something greater, the influence of a single species on the texture of the sea itself. By drawing clams from mud with suction alone, walruses rewrite the architecture of the benthos, proving that size and strength can serve the service of subtlety. In the end, the walrus is a paradox. A massive body that moves with delicacy, a predator that feeds with suction rather than teeth, a creature of ice that is reshaping the seafloor below. It is a vacuum engineer at the edge of the Arctic, a living reminder that survival in the coldest seas depends not only on size or blubber, but on the ability to transform pressure into power and patience into nourishment. In the radiant light of a tropical reef, color is everywhere. Corals fluoresce with neon greens and purples, shoals of damselfish glitter in flashes of silver, and sponges stand like towers in hues of scarlet and cobalt. Against this kaleidoscope of life, one predator appears more like a drifting ornament than a hunter. The lionfish glides forward, its long, filamentous fins trailing in the water like the tassels of a dancer's robe. Bands of white and chestnut stripes ripple along its body, perfectly symmetrical, hypnotic in their contrast. At first glance, it seems almost too conspicuous to be dangerous. But this is camouflage by audacity, beauty so bold that it disarms, drawing little suspicion from prey until it is far too late. With a slow unfurling of its fins, the lionfish begins to create a trap, and the reef itself seems to shrink around its victims. Unlike predators that rely on speed or stealth, the lionfish excels in control. It advances not with sudden lunges, but with the deliberate spread of its pectoral fins, which fan outward to form a broad, translucent wall. To a small reef fish, this curtain of motion is disorienting. It reduces escape routes, blocks lateral retreat, and narrows the prey's options until there is only one path: forward, into the waiting mouth of the lionfish. The maneuver is enhanced by coordinated herding tactics. A lionfish will use its fans to gently nudge prey against coral structures or the seafloor, corralling them into corners where flight becomes impossible. In some cases, multiple lionfish have been observed working together, forming semicircles that close around entire shoals, each fish acting as a living panel in a moving net. The strategy is slow, patient, and devastatingly effective. But the fins are not merely instruments of herding, they are also banners of warning. Embedded within the lionfish's dorsal, pelvic, and anal fins are spines tipped with venom glands. These spines are not actively injected like a snake's fangs, but act through pressure. When a predator or careless diver presses against them, the tissue sheaths retract, and venom is delivered into the wound. The toxins disrupt nerve signaling, causing searing pain, swelling, and in some cases systemic effects such as dizziness or difficulty breathing. While rarely fatal to humans, the sting is memorable enough to deter most would-be attackers. For reef predators, the cost of a single strike is too great to risk again. Thus, the lionfish carries not only a tool for hunting, but a shield of deterrence, making it nearly untouchable in the ecosystems it inhabits. The paradox of the lionfish lies in how its venom functions in ecology. Unlike the jaws of a barracuda or the suction of a monkfish, the spines are not tools of capture. They do not immobilize prey. Instead, they ensure the lionfish can hunt without interference. Few predators dare to approach, leaving the lionfish to dominate hunting grounds with little competition. In native ranges such as the Indo-Pacific, natural checks exist. Specialized predators and parasites keep populations balanced. But when lionfish were introduced, likely through the aquarium trade, into the Atlantic and Caribbean, those checks disappeared. There, the venom tipped the balance toward invasion. With no local species willing to challenge them, lionfish proliferated, consuming reef fish populations at staggering rates and disrupting food webs that evolved over millennia. To understand the scope of their impact, consider their nocturnal raids. As dusk settles, lionfish emerge from their daytime shelters beneath coral ledges and sponges. Under cover of darkness, they drift silently across the reef, their stripes breaking into fragments of shadow that mimic the fractured moonlight. Small fish, half asleep and sluggish, become easy targets. Studies have shown that lionfish can reduce juvenile reef fish densities by up to 90% in heavily invaded areas.
Each individual lionfish consumes dozens of prey items per day, and their diet is indiscriminate. Wrasses, damselfish, gobies, and even juvenile groupers all vanish into their mouths. This voracity reshapes reef communities, eroding the very foundation of biodiversity that coral systems depend upon. Their ability to thrive as invaders is not limited to venom and appetite. Lionfish possess remarkable reproductive capacity. Females can release egg masses every few days, with annual outputs numbering in the millions. The gelatinous egg sacs drift with currents, dispersing larvae over vast distances. Within weeks, new territories are seeded, and without natural predators to restrain them, populations expand unchecked. Combined with their broad tolerance for salinity and temperature, lionfish have colonized environments far beyond their native coral reefs, from mangrove lagoons to estuarine shallows. They are opportunists that flourish wherever structure and prey align.
Control efforts by humans have become a curious subplot in this ecological drama. Spearfishing derbies, organized culls, and commercial harvesting for food have all been attempted. Indeed, lionfish meat is safe and even considered a delicacy when the venomous spines are removed, leading some conservationists to promote "eat them to beat them" campaigns. Yet the scale of their reproduction and spread makes total eradication impossible. Instead, localized efforts can only slow their impact, creating temporary relief for reefs struggling under their pressure. It is an ironic twist. An animal admired in aquariums for its beauty becomes a menace in the wild, demanding human intervention to restore balance. From a biological perspective, the lionfish embodies the dangers of ecological imbalance. Its strategies, fin herding, venom defense, nocturnal hunting, are not inherently destructive. In its native waters, they are simply one predator's way of carving out survival in a competitive ecosystem. But when freed from the checks of co-evolved predators, these same traits become devastating weapons against naive prey and fragile habitats. It is a reminder that adaptation is context-dependent and that beauty and balance are inseparably tied to the communities in which they evolved. Still, beyond the headlines of invasion and control, the lionfish remains a marvel of evolutionary design. Its ability to manipulate space with its fins, to alter the very geometry of escape, highlights the subtle power of slow predation in a world where speed often dominates. Its venom, though defensive, has biomedical interest, with studies investigating its potential for novel pharmaceuticals. Even its bold striping, once thought purely ornamental, may serve multiple functions: warning, camouflage, and perhaps even recognition among individuals. The lionfish is at once ornamental and lethal, a creature that commands attention not by hiding, but by forcing everything around it to reckon with its presence. To watch a lionfish hunt is to see beauty turned into architecture. The reef becomes narrower, the prey's world smaller, until escape routes vanish into the expanding fans. Then, in a sudden strike, the mouth opens and the illusion of safety collapses. What moments before seemed a harmless drift of color reveals itself as a calculated trap. The lionfish teaches us that ecosystems are not only sculpted by raw speed or overwhelming strength, but also by the quiet power of space, timing, and deterrence. In the end, the lionfish is a paradox of the reef, beautiful yet destructive, slow yet devastating, ornamental yet armed. In its stillness lies control, and in its fans lies the power to collapse entire escape paths. Where it belongs, it is a predator balanced within a web of others. Where it does not, it is a symbol of how quickly balance can be lost. And so the lionfish drifts on, fins unfurled, a living fan trap whose beauty masks the devastation it brings when the curtain finally closes. On the shimmering shallows of tropical seas, where sunlight scatters in ribbons across sandy plains, an unassuming fish drifts just above the seabed. At first glance it seems vulnerable, almost comical in its rounded body and small fins. Yet hidden within this modest frame lies a repertoire of defenses and behaviors so remarkable that few predators dare test them twice. The pufferfish is a creature defined by paradox, slow but dangerous, fragile in appearance, yet armored by chemistry and architecture. It embodies two extraordinary strategies: an inner arsenal of toxin and inflation, and an outer performance of design so precise it rivals the artistry of humans. The most famous of its defenses is inflation. When threatened, the pufferfish transforms from a small edible shape into an oversized sphere bristling with spines. The mechanics of this expansion are as fascinating as they are effective. Beneath its skin lies a highly elastic stomach and abdominal wall capable of stretching several times its resting size. By rapidly gulping water, sometimes air if caught above the surface, the fish inflates in seconds, ballooning into a globe that few predators can swallow. Spines that lie flat when at rest jut outward, creating a prickly barrier. The sudden increase in size not only prevents ingestion, but startles attackers. What seemed like a snack explodes into a hazard. This inflation, however, is not a mere party trick. It exacts a physiological cost. The bloated fish struggles to maneuver, its gills compressed by internal pressure. It is a temporary gamble of immobility against immediate survival. a strategy that only works because few predators are willing to risk the consequences of pursuing an inflated target. The true danger lies deeper, in the tissues themselves. Many species of pufferfish carry one of the most potent toxins known in nature, tetrodotoxin. Originating not from the fish's own cells but from symbiotic bacteria housed within its body, this neurotoxin binds to sodium channels in nerve membranes, blocking the electrical signals that allow muscles to contract. For predators that ignore the warning of inflation and attempt to eat a puffer, the results can be fatal: paralysis, respiratory failure, and death. To put the potency into perspective, a single pufferfish contains enough tetrodotoxin to kill several humans, and yet it shows no ill effects itself, having evolved resistance at the molecular level. The logic of such a defense is clear. Predators learn quickly. A single encounter, whether lethal or merely sickening, imprints a lesson that spreads across generations. Few animals make the same mistake twice. This combination of physical inflation and chemical defense creates a layered survival system. If the sudden ballooning does not deter, the toxin enforces the consequence. Yet the pufferfish is not only about defense, it is also an architect. Among the most extraordinary behaviors in the animal kingdom is the construction of intricate sand mandalas by male white-spotted puffers. In shallow coastal waters off Japan, these males spend days crafting elaborate circular nests on the seafloor. Using their fins, they sweep sand into ridges and valleys, forming geometric patterns several meters wide. The design resembles a flower or starburst, with symmetry so precise it astonishes biologists. But this is not art for its own sake. It is engineering in service of reproduction. The purpose of the mandala is to attract females. The ridges amplify water flow, channeling currents toward the central hollow where eggs will be laid. Fine shell fragments and bits of coral are carefully placed to stabilize the structure, preventing collapse under waves. When a female inspects the design, she is not merely judging aesthetics. She is assessing the health, stamina, and precision of the builder. Only a male with strength to maintain the circle against currents, with attention to detail in pattern, and with endurance to guard it, can be considered a worthy mate. In this sense, the puffer's architecture is both display and test, an ecological advertisement of genetic quality. This behavior raises intriguing questions about cognition in fish. The ability to measure, adjust, and maintain such complex structures suggests spatial awareness and memory far beyond what is typically attributed to small reef species. Each circle is unique, yet all follow principles of hydrodynamics, proof that evolution has hardwired not just instinct, but engineering solutions into the brain of the pufferfish. These circles endure only until the eggs are laid and fertilized. After that, the currents reclaim the sand, erasing the design as if it never existed. But for the brief period of courtship, they stand as monuments to the hidden intelligence of a fish often dismissed as little more than a novelty. The puffer's beak-like jaws add another layer to its story. Formed by fused dental plates, these jaws are powerful tools designed for cracking the shells of crustaceans and mollusks. Clams, crabs, and snails, usually well protected against smaller predators, are no match for the crushing bite of a puffer. This specialization places the fish in a unique ecological niche, controlling populations of hard-shelled invertebrates that might otherwise dominate reef environments. Combined with its defenses, this diet ensures the puffer remains both predator and prey in delicate balance. From an evolutionary perspective, the dual strategies of defense and display highlight a recurring theme in nature. Survival often requires more than one solution. Inflation and toxin protect the individual, while architecture and beak adapt it to its environment and reproductive success. The convergence of these traits demonstrates how multiple selective pressures, predation, competition, reproduction, can sculpt a species into something far stranger and more versatile than a single adaptation could achieve. Humans inevitably enter this story. In Japan, the pufferfish is both feared and revered as fugu, a delicacy prepared only by licensed chefs. The danger of tetrodotoxin is part of the cultural mystique, a reminder that beauty and peril often coexist in the natural world. This relationship underscores the tension between our admiration for unique adaptations and the risks of exploiting them. Beyond cuisine, the toxin has drawn interest from biomedical research, with studies exploring its potential as a painkiller far stronger than morphine, but without addictive side effects. In this way, the puffer's defense mechanism, honed by evolution, may one day provide tools for human medicine. Ecologically, pufferfish play subtle roles in reef health. By preying on invertebrates that graze on coral, they help maintain the balance necessary for reefs to flourish. Their presence is part of the intricate web of interactions that sustain biodiversity in coastal systems. Remove them and the pressure shifts, often with cascading effects. This makes them not only intriguing curiosities, but integral players in the fragile balance of marine ecosystems. In the final analysis, the pufferfish embodies two extremes: chemical defense and architectural display. It is a creature that inflates itself into absurdity to ward off danger, yet invests meticulous effort in crafting beauty beneath the waves. To a predator, it is a lesson in regret. To a female puffer, a geometric masterpiece is a promise of strong offspring. To us, it is a reminder that survival is rarely straightforward. Nature equips its creatures with tools both subtle and spectacular, and in the case of the pufferfish, those tools range from toxins that can silence nerves to mandalas that can inspire wonder. Floating just above the sand, a puffer drifts between invisibility and spectacle. In one moment it is a small edible fish, in the next a spiked balloon too dangerous to touch. And in yet another, it is an engineer sculpting the seafloor into a perfect circle, a transient monument erased by the sea but written permanently into the code of survival. In its chemistry and its architecture, the pufferfish teaches us that life in the ocean is defended not only by teeth and speed, but also by patience, artistry, and the ability to turn the very physics of water and sand into a survival strategy. In the warm shallows of the Indo-Pacific, where coral reefs sprawl like living cities across the seafloor, a shadow moves with surprising grace for its size. At first, the silhouette could be mistaken for a drifting boulder, or a large turtle gliding between coral heads. But as it emerges into shafts of filtered sunlight, its true form is revealed. A humphead wrasse, also known as the Napoleon fish, one of the largest reef fish in existence. Its body shimmers in hues of turquoise and emerald, patterned with labyrinthine lines that ripple across thick lips and massive scales. Atop its forehead, a pronounced hump protrudes, a feature that grows more imposing with age, lending the fish its name and unmistakable profile. At nearly 2 meters in length and weighing as much as 200 kilograms, it is a giant among reef dwellers. Yet for all its bulk, the wrasse is more than an impressive presence. It is a problem solver, an ecosystem caretaker, and a predator with a taste for prey most fish dare not touch. The feeding behavior of the Napoleon fish sets it apart from nearly all other reef hunters. Its jaws, backed by powerful pharyngeal muscles and reinforced with bone, are capable of feats that verge on the mechanical. This is a fish that does not merely graze or snap at passing prey, it smashes through armor. Hard-shelled clams, which most fish cannot even dent, are no obstacle for this wrasse. With deliberate force, it lifts a clam in its mouth, swims to a suitable outcrop of reef or rock, and slams the shell against the surface until it cracks. The behavior is strikingly reminiscent of tool use, leveraging the reef itself as an anvil to solve the problem of accessing food locked behind defenses. Once broken, the clam's soft tissues are stripped out with ease, consumed by jaws designed not just for capture, but for crushing. But the wrasse's diet extends beyond clams. One of its most important roles on the reef is as a specialist predator of toxic or otherwise avoided species. Chief among these is the crown-of-thorns starfish, a spiny invertebrate that feeds voraciously on living coral tissue. In outbreak years, swarms of crown-of-thorns can devastate entire reef systems, stripping corals bare and leaving behind fields of skeletal rubble. Few predators can handle them. Their long, venomous spines are effective deterrents against most fish, and their tough body walls resist casual bites. Yet the humphead wrasse has evolved to consume them with little difficulty. With its crushing jaws, it bites through the starfish's armored surface, flipping it to expose vulnerable tissue. Digestive adaptations allow it to tolerate the cocktail of toxins laced into its spines. By feeding on crown-of-thorns, the wrasse acts as a critical check against outbreaks, safeguarding the coral architecture on which countless species depend. In this sense, it is not merely a predator, but a keystone custodian, one whose appetite preserves the balance of an entire ecosystem. The paradox of this fish lies in its gentle demeanor. Despite its fearsome jaws and colossal size, the Napoleon fish is not a reckless aggressor. Its movements are measured, its strikes calculated. Unlike a barracuda's explosive lunge or a lionfish's slow entrapment, the wrasse feeds with a kind of deliberate precision. It chooses targets carefully, often focusing on species that other reef inhabitants avoid. Toxic sea hares, boxfish, and even certain species of toxic sea cucumbers all fall within its diet. This specialization reduces competition, carving out a niche where the wrasse's strength and tolerance for chemical defenses give it exclusive rights. In ecological terms, it fills the role of a cleaner of the reef's most dangerous pests, converting problems into fuel for its own survival. Its biology is no less fascinating than its role in ecology. The humphead wrasse undergoes a life history strategy known as protogynous hermaphroditism. Individuals begin life as females, with some later transitioning into males as they grow larger and older. This sex change is not random, but influenced by social dynamics within wrasse populations. In areas where dominant males are absent, the largest females may shift to male, taking on the role of breeders and defenders of spawning grounds. This system ensures that reproduction can continue even if certain demographics are disrupted, but it comes with a crucial vulnerability. The largest males are disproportionately important. Because they are the ones that have already transitioned, their removal through fishing can collapse reproductive networks. Protecting big males, therefore, is not simply a matter of conserving impressive individuals. It is essential to preserving the population's long-term survival. The transition itself is a marvel of physiology. Hormonal changes trigger the restructuring of gonads, the reconfiguration of behavior, and even shifts in coloration and head morphology. The hump, so prominent in older males, becomes more defined, and dominance behaviors emerge. This transformation reflects the remarkable plasticity of fish biology, an evolutionary solution to the challenge of ensuring genetic continuity in environments where mortality is high and conditions unpredictable. Yet it also highlights the fragility of the species in the face of human exploitation. Removing the largest individuals does not merely reduce numbers, it undermines the very system by which the wrasse sustains its population. The Napoleon fish's ecological importance has not shielded it from human threats. Its size and beauty make it a target for spearfishing, while its flesh, especially lips, is considered a delicacy in parts of Asia. These pressures, combined with slow reproductive rates, have caused severe declines in populations across much of its range. The species is now listed as endangered, its future uncertain. Conservation efforts increasingly recognize the dual importance of the wrasse, both as a charismatic flagship for reef protection and as a functional guardian against coral decline. Marine reserves where wrasse populations are protected show greater resilience against crown-of-thorns outbreaks, demonstrating the direct ecological benefits of conservation. Seen within the living tapestry of the reef, the humphead wrasse embodies the principle that strength can serve subtle ends. Its smashing of shells may seem brutal, yet it enables the recycling of nutrients locked away in armored prey. Its consumption of toxic starfish is not violent excess, but necessary regulation of populations that would otherwise overrun corals. Even its unusual life history, shifting from female to male, is a kind of flexibility in service of balance, ensuring reproduction adapts to social and environmental shifts. It is a giant that does not dominate through fear, but through the careful application of power and persistence. To watch a humphead wrasse at work is to witness the fusion of raw strength and refined problem-solving. A clam shattered against stone, a venomous starfish dismantled spine by spine, a reef preserved through the appetite of one massive fish. These are not isolated acts, but the rhythm of an animal woven into the health of its environment. It reminds us that ecosystems are maintained not only by abundance and diversity, but by the presence of specialists willing to take on the hard, toxic, and armored challenges others avoid. Without them, balance falters. In the end, the Napoleon fish is both enforcer and caretaker, a predator whose bite resonates far beyond its meal. It safeguards coral reefs by consuming their enemies, recycles locked-away energy through shell smashing, and sustains its lineage through remarkable flexibility of sex and role. To call it a gentle giant is not sentimentality, it is accuracy. For beneath its imposing frame lies not the chaos of unchecked aggression, but the steady problem-solving presence of a reef guardian. In every clam cracked and every starfish eaten, the humphead wrasse demonstrates that survival is not only about feeding oneself, but about maintaining the foundation upon which an entire ecosystem depends. On a sunlit reef slope, the current moves gently across an expanse of waving tentacles. Each tendril pulses with hidden danger, armed with thousands of microscopic harpoons capable of injecting venom into anything that dares to touch. To most reef fish, the sea anemone is a death trap, a living fortress that promises certain paralysis and suffocation to any that drift too close. Yet through this electrified thicket of stinging cells, a tiny orange and white fish darts with utter confidence. The clownfish slips among the tentacles as if immune to their menace, pressing its body against the lethal arms in a display that to any other creature would mean immediate pain. What appears to be recklessness is in fact one of the most extraordinary alliances in the ocean, a partnership between predator and prey, plant and animal, fortress and farmer. The secret to the clownfish's immunity lies in its skin. Unlike other reef inhabitants, it coats its body in a specialized mucus layer that prevents the firing of nematocysts, the stinging cells embedded in the anemone's tentacles. This protection is not innate from birth, it must be acquired. Young clownfish entering an anemone do not swim in freely but perform a ritual of acclimation. They touch the tentacles gingerly, retreat, then return, rubbing their bodies against the stinging arms again and again. In time, their mucus incorporates chemical cues from the anemone itself, masking the clownfish as part of the host's own tissue. Only then can the fish nestle deep within the tentacles without fear. This gradual acceptance is essential. A rash approach means death. In this way, the clownfish earns its citizenship in a fortress of venom. Once inside, the partnership transforms the lives of both organisms. For the anemone, the clownfish is more than a tenant. It is a guardian and caretaker. The constant fanning of the clownfish's fins improves water circulation, delivering oxygen to the anemone's tissues and dispersing waste products. Their bold, darting behavior drives away butterfly fish and other species that would nibble at the anemone's tentacles. In return, the fish receive the ultimate protection, a home no predator dares enter. Even large hunters such as groupers and moray eels, capable of swallowing clownfish whole, will not risk the anemone's lethal sting. Within this lethal fortress, the clownfish establish their nursery, raising eggs and young in one of the safest refuges the reef can offer. The economic exchange between clownfish and anemone extends even further. Clownfish excrement contains nitrogen and phosphorus, vital nutrients for the symbiotic algae that live within the anemone's tissues. These algae, in turn, photosynthesize, producing energy that sustains the anemone itself. In effect, the clownfish operates as both defender and farmer, fertilizing the algae that fuel the anemone's growth. Scientific studies have shown that anemones with resident clownfish grow larger and healthier than those without, a striking demonstration of mutualism where both partners enhance each other's survival. What begins as a defense pact becomes a miniature nutrient cycle, a closed farm system built into the very arms of a predator. Within the safety of this farm lies an even stranger story, that of the clownfish's social order. Life in an anemone is governed by a strict hierarchy. At the top is a dominant female, largest of the group and responsible for reproduction. Beneath her is the breeding male, smaller but still privileged. Below them, a ladder of subordinate males exists, each waiting for opportunity. When the female dies or disappears, the breeding male undergoes a remarkable transformation. His sex changes, and he becomes the new female. From the ranks of subordinates, the largest then ascends to breeding male. This protandrous system, male-to-female sex change, ensures that the group always maintains a breeding pair, no matter the losses. It is a hierarchy enforced not by constant aggression, but by social restraint. Subordinates suppress their own growth, staying small and non-reproductive until a vacancy appears. The anemone thus functions as both fortress and monarchy, with power and sex written into its walls of stinging cells. This social structure has profound implications for survival. By limiting breeding to a single pair, the clownfish avoid overcrowding their host. The anemone's resources are finite. Too many mouths would strain the mutualism. Instead, the hierarchy keeps numbers balanced, ensuring the health of both partners. It is a rare example of natural population control that arises not from external predators, but from internal cooperation and competition. In evolutionary terms, it is a safeguard against over-exploitation, a system that maintains stability within a fragile alliance. For all its charm, the clownfish-anemone partnership is also a story of vulnerability. Anemones depend on the algae within their tissues, and these algae are sensitive to temperature. During periods of ocean warming, they are expelled, leaving the anemone pale and weakened, a process known as bleaching. Without healthy hosts, clownfish lose their fortresses, exposing them to predation. Similarly, human collection for the aquarium trade has removed countless individuals from reefs, threatening local populations. The fragility of this partnership reminds us that even the most perfect alliances can falter under environmental stress. Their survival is tethered to the broader health of coral reef ecosystems, themselves increasingly endangered by climate change, pollution, and overfishing. Yet the resilience of this alliance is also remarkable. In protected areas where reefs remain intact, clownfish and anemones thrive in abundance, their partnership as vibrant as ever. Watching a group of clownfish weave among anemone tentacles, darting out to chase intruders before retreating back to safety, is to witness a choreography refined by millions of years of co-evolution. Each fin beat and each chemical cue represents the culmination of a long evolutionary negotiation where two very different organisms found a way not only to coexist, but to prosper together. There is even a curious irony in the clownfish's name. Popular culture has cast them as clowns of the reef, colorful jesters darting nervously among tentacles. But their reality is far more serious. They are farmers, defenders, engineers of nutrient cycles, and practitioners of one of the most extraordinary sexual strategies in the animal kingdom. Their bright colors and bold behavior are not comic relief, but evolutionary declarations. Here lies a species that has turned danger into sanctuary, a venomous gauntlet into a nursery. To truly understand this partnership, one must imagine the reef without it. Without clownfish, anemones suffer, growing smaller and weaker. Without anemones, clownfish are stripped of protection, exposed to predators that quickly reduce their numbers. Each partner relies so fully on the other that their survival has become intertwined beyond separation. They represent one of the purest examples of symbiosis in the ocean. Two species, entirely different in form and function, yet bound together in a relationship that transforms lethal tentacles into life-giving shelter. In the end, the clownfish and anemone remind us that survival is rarely solitary. In a world where most animals are locked in constant struggle, these two have found success through alliance. A fish immune to stings, an anemone defended and fertilized, a farm built within a fortress. Their partnership is at once bizarre and elegant, a living demonstration that ecosystems are networks of cooperation as much as they are arenas of conflict. Where danger once stood alone, a nursery now thrives.